In today's lesson, we're going to take a look at more permutations, but with restrictions and repeated elements. And again, we actually have looked at a few restrictions in the past lesson already, so that's not really a new thing. We're just going to look at basically some tips and tricks on how to solve problems that have a little bit more detail to them. The first thing I want to talk about is direct versus indirect reasoning. And depending on who's teaching you these, sometimes there are slightly different names for them, but I will use direct and indirect. If you're not familiar with these names or another teacher has taught them to you under a different name, I'm sure you'll recognize them. So these two ideas are not just specific to permutations. These are actually going to be used throughout the entire rest of the course. So they're very important ideas to understand. Direct method of solving a problem is to look for the thing that you're looking for. I realize that sounds like almost a ridiculous statement because it seems too simple to be true, but it is. So for instance, if I had a class of students, let's say I've got 30 students in the class, and someone said, how many guys are in the class? I have a couple of options. My first and most obvious option is to count the guys in the class. So I count them up and I get some number. Let's say there's 10. Um, that would be the direct method. The indirect method is by looking at an entire group and subtracting off the ones that you do not want. As I'm saying this, I realize that this example is going to get me into some trouble. When I say I do not want the girls in the class, that does not mean I actually don't want girls around. It just means that within this context of a question, we're not looking for the number of girls. So if I wanted to know the number of guys, I could take the entire class, subtract off the number of girls, and I'd be left over with the number of guys. So 30 in the class minus 20 girls would give me 10 guys. Now, is one method better than the other? And this is a question I'm always asked. And the answer is it depends on what it is you're looking for and how it is you want to look for it. So for instance, if I'm asked how many students in the class are wearing glasses, if there's only like 3 or 4 students who wear glasses, it's easiest to count them. That makes sense. That would be the direct method. If I'm asked how many students are wearing glasses and almost the entire class is wearing glasses, then it's usually easier for me to count the students who aren't wearing glasses and subtract it off of the total. And so there is no right or wrong answer to which one should I use. Is one method going to give me a faster, easier answer than the other method? And I will say that in some situations, not a lot, but some, one of these two methods will be so much easier than the other to the point where it's really the only logical way to approach the problem. And then there'll be other questions where it really doesn't make any difference at all. So if my class was 15 girls and 15 guys, direct versus indirect makes no difference. If there was two of one gender and everyone else was different, then it definitely will make a difference on how much easier it is to do the problem. And then there could be or many more significant problems where we're looking at big restrictions and one method will be better than the other. But let's jump into an example here and just see how they work, and we'll worry about which one's better or worse afterwards. So for example 1, how many words can be made from the letters in the word math? Well, we've done this one before. It's 4 different letters. We're rearranging them. So that's just going to be 4 factorial, which is 4 times 3 times 2 times 1, or 24. For part B, how many words can be made from the letters math that start with the letter M? So I'll draw the 4 lines to represent the 4 choices I have to make, first, second, third, and fourth letter. And I'm going to put the restriction underneath here. Again, no particular format as far as what I write. I just putting this down to remind myself that first letter should be an M. That gives me 1 choice there, 3 choices there, 2 choices there, and 1 choice there. And then we just multiply those numbers together, 1 times 3 times 2 times 1, and that should equal 6. So there'll be 6 different six different words we could make. And again, I probably should have put word in quotation marks. These don't have to be real words, but there's 6 different orders of letters we can get from, 6 different orders of letters we could get from this. And then we want to find the number of words that can be made from the letters in the word math that do not start with the letter M using direct reasoning. And of course, we're going to do indirect reasoning after that as well, so we'll kind of consider these together. Okay, so to do it directly, I would say that the first letter cannot start with an M. So underneath my line, I could write this a few different ways. I could put no M, or in this case, I think I'm just going to put ATH. So it's got to be one of those three letters. So I have three choices for that, three choices for that, two choices for that, and one choice for that. Three for the first letter because it can't be an M, so I only have three choices. And then once I put a letter down, I can have either of the other two or the M, so I've got three choices for my second letter, and then similarly two for my third and one for my fourth. Multiplying those together gives me 18 times 2 is, 9 times 2 is 18. So that's a direct approach to the problem, which seems quite reasonable. And then doing the exact same problem, which words start with, do not start with an M, using the indirect reasoning, we can just put down all minus start with M. And we don't have to write that. Again, I'm just writing this down to show you where my logic comes from. And there were 24 possible words, and 6 of them started with an M, and that gives me 18. So now the answers will always be the same regardless of whether you use direct or indirect reasoning. The question is just going to be, does one of those answers or one of those solution methods get me to the answer faster? And again, the only way to really see this is to kind of do some practice with them and try a few examples, and then you start to recognize, okay, I can approach it this way or this way. This way is going to be shorter. Sometimes you have to do 2 or 3 calculations to do it one way, and 6, 7, 8 calculations to do it the other. Both of them will work, but one of them will get you to the answer faster. Okay, so for example 2, this one's at least a little bit more interesting. Say that we wanted to find how many 4-letter words can be made from all 26 letters of the alphabet with no repetition. So we can't have the same letter appear more than twice, that contain at least one vowel. At least one vowel. So we're going to try and solve this both indirectly and directly. I'm actually going to start with the indirect method first. Spoiler alert, this is going to be the easier method. So the indirect reasoning would be to take all possible words, at least all 4-letter words. I'm not going to write down all the details here. I think the context of the question is good enough. But all the 4-letter words we can make, and I'm going to subtract off the ones with no vowels. That seems easy enough. How many words can we make with 4 letters out of 26? The answer is just 26 pick 4. So 26 pick 4, we'll punch that into the calculator in a moment. How many words can I be making with 4 letters that have no vowels in them? Well, there are 5 vowels. Again, a reminder, we don't consider Y a vowel, even though sometimes it is in English. We're just going to do A, E, I, O, or U. So we have 5 possible letters that could be there. And since we have none of those appearing in our word, really what it's saying is there's 21 consonants or 21 other letters left over that we can choose from. So this is just going to be 21 pick 4. Okay, neither of those two things is particularly complicated. So now I just pull out the calculator and do 26 pick 4, which is 358,800, and then 21 pick 4, which is 143,640. And then if I do that subtraction without screwing up, I should get 215,160. Okay, so that's the number of possible 4-letter words that I can make that have at least one vowel in them. So again, the way to think about this one is to think about making a list of all of the possible words and then crossing out the ones that have no vowels in them. That's essentially what we're doing with the indirect method. Make a list of everything, cross out the ones we don't want. And then what we're left with is ones that we do want. Okay, now part B, I put down try solving this using direct reasoning. I'm going to talk you through this one. I'm not going to write a lot down, and I think you'll see why. We have to make a 4-letter word that has at least one vowel. So let's assume that the first letter is a vowel. So if the first letter is a vowel, I have 5 options for that. Well, how many options do I have for the second letter? Now, it seems pretty obvious. The second letter can't be the same as the first letter, so there's 25 options left. But wait a second. Those 25 options, one of them, well, 4 of them are vowels. So what if you got a vowel there? Because if you got a vowel in the second spot, you have 2 vowels already. But since you only need one, having a vowel in the second spot means you didn't need a vowel in the first spot. So the first spot could have been any of the 26. Okay, that leads to kind of a big question. How do we deal with that? This is where I'm going to talk you through without writing. If we want to approach this question directly, what we have to do is add up all the different cases where there's at least one vowel. So that would be, and I realize you can't see me doing this, but I'm going to try and keep track on my fingers. Actually, you know what? I'm going to make little tick marks here just so that you can see the problem we're going to have with this. If it needs to have at least one vowel directly, I could have a vowel in the first spot and no vowels in the second, third, or fourth. So that's one situation, one case. Or I could have a vowel in the second spot, but not in the first, third, or fourth. Or I could have a vowel just in the third spot or just in the fourth spot. So there's 4 cases. But those 4 cases assume that I have exactly one vowel, not at least one vowel. I could also have vowels in the first and second spots, first and third, first and fourth, second and third, second and fourth, third and fourth, first, second, third, first, second, fourth, first, third, fourth, second, third, fourth. I may have made too many tick marks. I'm not even caring. Oh, wait, but I could have just 2 vowels. Sorry, that was exactly 3 vowels. Now I can do exactly 2 vowels. Those could appear in the first and second, first and third, first and fourth. Yeah, I'm losing track already. Did I do 2 already? I'm not even sure anymore. The point is, there's a whole bunch of different cases. Oh, and then there's like that one case where all of them are vowels. So the point is there's way too many cases here to consider. All of these would require a calculation that's longer than the first part A version, the indirect reasoning. So I think it's safe to say that regardless of how many tick marks I actually made and what I lost track of and what I didn't, it's too long to do it this way. It's possible, but it's going to be really, really long. So we don't want to have to do this one during using direct reasoning. All right, moving on to the second approach of solving questions today is something I like to call clumping. Again, not a textbook term, just a term that I like to use to represent what's actually happening. And the idea of clumping is that we're going to take some of the objects in our group and we're going to consider them to be one single object. So we're going to treat them like they're stuck together in a clump, if that makes sense. Okay, so for example 3 part A, we have how many words can be made from the letters in math where the T and the H are beside each other? Okay, so the easiest way to do this is to not think of T and H as separate letters, but to think of them as one thing. To think of this as a 3-letter word, M, A, and TH, TH being one of the letters. So there's essentially 3 clumps in this question. There's a clump that's just M, a clump that's A, and a clump that's TH. So we're going to think of this as like it's 3 cards, like we're doing our sign problems again. But we're going to put the T and the H on 1 card. If I do that, I can think of this as rearranging 3 things instead of 4. So it's just going to be 3 factorial. There is one more little trick to this though, and that's that I'm going to have to multiply by the number of ways of rearranging things within the clump. So while the th can be thought of as one thing, it could be a th or it could be an ht, which is 2. Now, I should point out that this is actually going to be 2 factorial. If there were 3 things in the clump, so it was like ATH altogether, then there would be 6 ways of arranging those 3 letters in the clump. So even though it is times 2 and 2 factorial are the same thing, I'm going to point out that this is the number of clumps. And this is, ooh, I can't spell today. That's a lie, I can't spell any day. Rearrange in a clump. And if there were more than one clump, I would have, like, let's say I put the m and the a together, then I could multiply by 2 factorial again for the number of ways of arranging things in that clump. So things in clumps can always just be treated like their own little thing. Do the number of ways that you can arrange the clumps, and then do the number of ways that you can rearrange things within clumps. Now in this case, that happens to be 6 times 2, so there'd be 12 possible ways. Okay, how many ways, how many words can be made if the T and the H aren't beside each other? Well, we could try to do this, but again, if we do it directly, the T and the H, if they're not beside each other, would have to be in the first and third, or first and fourth, or second and fourth spots, and could be rearranged so it could be the T then the H or the H then the T. So there's a few different cases that we'd have to deal with there. Or what I could say is indirectly, it's just all possible cases minus the versions where they're together. And there were 24 possible words we could make with 4 letters rearranged. We just said there were 12 where they were together, so there are 12 where they are not together. And in this case, indirect reasoning kind of wins out again. All right. Last kind of idea for the day is duplicate objects. So far we've been doing things like rearranging words that have 4 letters or 6 letters where they're all different. Here what we're going to do is rearrange words where the letters are the same. And I want to point out that words are an easy thing to do, but there's lots of different examples of things that could be arranged with duplication that we're going to see in examples in a moment. But for now, here's what I want you to think about. Let's pretend that just for a second, instead of having 2 N's in it, the word funny had a capital N and a lowercase n. So pretend that those are actually 2 different letters. If they were different letters, then FU capital N lowercase n y could be thought of as a 5-letter word. So 5 factorial ways of rearranging. However, capital N lowercase n, the order of those doesn't matter. So it could either be capital then lower, or it could be lower than capital, which means there's 2 different ways I could rearrange those. That or that, regardless of where they fall in the word. And what that means is that I have 2 times too many answers. So it's not going to be 5 factorial. It's actually going to be 5 factorial divided by 2 factorial. And then 5 factorial is 5 times 4 times 3 is 60 once we've divided out the 2. Okay, so now I realize I said there were 2 ways of rearranging it, but I wrote down 2 factorial. Again, 2 factorial is the number of ways of arranging 2 different letters. So what we're saying is we're pretending they're different, and then we're unscrambling it by knowing that they actually are the same. Same logic with the word mummy. The word mummy has 5 letters again, so it could be thought of as 5 factorial arrangements if they were all different. However, the 3 M's can be rearranged in 3 factorial ways, so I just do 3 factorial on the bottom. Now, if you're having trouble with the logic and seeing it on these, the actual format's pretty simple. The first one had duplication of 2 things, so we put 2 factorial on the bottom. This has duplication of 3 things, you put 3 factorial on the bottom. When you do this one, you get 20. And I'm going to point out that if you had a 5-letter word where all the letters were M's, so, just like, something looks tasty, that would be 5 factorial over 5 factorial, which would be 1, which makes sense. There's only one way to arrange 5 M's, and that's M, 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 M. Okay, this last one has a little bit more duplication in it. In fact, it has 1, 2, 3, 4, 5, 6 letters. So if they were all different, it would be 6 factorial. But it has 3 A's and 2 N's. And then the way we treat this is exactly the same as we treated the first two, except there's now 2 of them. The 3 A's can be arranged in 3 factorial ways. The 2 N's can be arranged in 2 factorial ways. And then from there, we could just do 6 times 5 times 4 divided by 2. 6 times 5 is 30 times 4 divided by 2 is 60, I believe. Hopefully that's correct. So it turns out that the number of ways of rearranging funny is the same number of ways as rearranging banana, despite the fact they have different numbers of repetitions and they are actually a different number of letters. But that's it for when we've got repeated elements. We simply divide by anything that's repetition. Factorial, of course. All right, so example 5, the same idea but without letters. This, by the way, is exactly how I used to do my lunches when I was a younger teacher and really, really lazy. I would just go to the store, buy a whole bunch of frozen TV dinner type things, take them to school, throw them in the freezer in our math office, and then I would just take them out and eat them every day. And I didn't have to remember to like take my lunch every day. I just took a bunch for like a week or two and then kept going until they were gone. Okay, so I bought TV dinners to school to eat. I brought TV dinners to school to eat for lunch for the next 2 weeks, which is 10 days. I have 5 beef, 3 chicken, 2 pasta. How many different ways can I arrange my lunches? So if these were 10 different meals, I could treat them as 10 different meals and say that there'd be 10 factorial ways of eating my lunches. However, we have some repetitions here. So the 5 beefs might seem like 5 different things, but they're all identical. So I just do 5 factorial on the bottom. And then we have the 3 chickens, makes us use a 3 factorial on the bottom, and the 2 pastas gives us 2 factorial on the bottom. Now this one, I'm going to actually just do out manually, at least partially. So the top is going to be 10 times 9 times 8 times 7 times 6. And I'm not going to worry about the 5 factorial on the bottom. I'm going to use it to cancel out the 5, 4, 3, 2, 1 on the top. Unfortunately, I still need to deal with the 3 factorial and the 2 factorial. Again, not writing the ones down because they don't actually do anything. And then from there, I can make a couple of little observations to make my calculation slightly faster. At least it would be if I wasn't talking through it completely. But the 3 times 2 cancels with the 6. And the 2 cancels with, honestly, any of the even numbers on the top, but I'm going to cancel the 8 and make it 4. Now that I have that, I can say that the top is 10 times 9 times 4 times 7. 4 times 7 is 28. 9 times 28 is 252. Times 10 is 2,520. And of course, by all means, you're welcome to use a calculator. In fact, I would like you to use a calculator right now. Humor me, if you will. And I'd like you to punch this into your calculator. Punch that into your calculator and let me know what your answer is. So I'm going to let you do that. I'm going to pause for a second. Let me know your answer. Okay, so I'm going to just out of curiosity, if anyone got this answer and is very confused, oops, let me switch back to a color that is easier to read. Come on, blue. If anyone got this answer right here, 362,880. Obviously, that's not the right answer because we know the right answer is right there, or I hope that's the correct answer. But if 362,880 is what you got, This is one of those making sure you understand how to use your calculator. So I'm going to actually verbally say what happens here, and hopefully that will explain why you're getting the wrong answer. So when I read that out, I would read that as 10 factorial divided by 5 factorial times 3 factorial times 2 factorial. However, if you punch it into the calculator that way, the calculator takes that as 10 factorial divided by 5 factorial times 3 factorial times 2 factorial. So it moves those 2 factorial and 3 factorial to the top. That is not what you want to do. You want to put them on the bottom. So you've got a couple of options. The easiest way for most people would be put a bracket around the bottom, or you could do the 10 factorial divided by 5 factorial, hit equals, then divide by 3 factorial, hit equals, then divide by 2 factorial, hit equals. Your choice. But I do want to point out that this right there is not the correct answer. And if you're getting it, that's why. It's basically a BEDMAS issue. So just a warning, if you're getting something way off the answer, there's a good chance that there's something like that you've plugged into your calculator that is not actually what you mean it to be. All right, that said, I've shown you, I think, all there is to show you when it comes to restrictions and repeated elements, at least at this point in the course. So I'll let you try some problems, and hopefully you'll learn a little bit more from them, because there's always a little bit to learn from the actual problems that I don't cover in the lessons, because there's a whole infinite number of possible things that you could have come up. And the best way to learn those things is to see as many examples as possible. So give them a shot, and if you need assistance, let me know. Have a good day.